Yeah, so looking at the first problem, here we're given that they say on this problem, let A be equals to the sets A, B, C, the elements A, B, C, define a relation R. Then they say where R is equals to BB, CA, AB, AC, BC, BA, CB, and CC. Then they say that we should determine whether R is reflexive, symmetric, and transitive, right? So the second one, which they say, if we are given R on Z, where X minus Y is equals to 4, and we're given a relation R defined on Z where XY is an element of R, which is the same thing as saying X is related to Y. If and only if X minus Y is equals to 4, and we should also determine whether R is reflexive, symmetric, and transitive. So we're gonna check in both ways how to determine this, right? How to determine whether R is reflexive, symmetric, or transitive in both ways. So starting with the first one, we are given this set, right? And they say that we are given, they say here that R is BB, CA, AB, AC, and so on. So we must first check whether this is reflexive, symmetric, or transitive, right? So for us to check for reflexive in this manner, remember reflexive says that a set should be related to itself, right? A set should be related to itself. That's how we check reflexive. Then if a set is related to itself, it means that that element is reflexive. So let's check here. The elements that we're given here, we're given A, B, C. So it means that for this to be reflexive, we must have AA, we must have BB, and we must have CC. You see, because we're given three elements, A, B, C. So each element there should be related to itself. But if we check on this, we do have BB, we do have CC, but then we do not have AA, right? So we can now say that we can come in, write a reason here to say, let me erase this. We can write a reason to say here that we can say this. We say that A, let's say for R to be reflexive. So I'm just gonna write this right and show that for R to be reflexive. So remember I said that for R to be reflexive, what must happen is that if we take X, let's say for each X, or for all X element of this A, you say right now, for this it must occur that X is an element of R. You say right. Then when we check here, what we are given, we do have that BB and also CC is an element of R. We do have this. We say right, we do have that AA and BB is an element of R. But AA is not. So we do have here that BB and CC is an element of R, but AA is not an element of R. Hence, R is not reflexive. Hence, R will not be reflexive. We say right. And then, now for us to check symmetric, we're going to come and say for R to be symmetric, we know that for R to be symmetric, it should occur that for all xy element of R, if we take xy element of R, it should occur that y x should also be an element of R. You see that for this to be symmetric. Hence, if we check here, can you please mute your mic? If we check here, we are saying that if we take two elements, it should happen that this should also be an element of R. So in other words, here we're given three elements, right? And we're going to take them 2 by 2. So if I take AB, it should happen that BA should also be an element of that set, right? So let's check here what we have. First, we're given AB. Let's start with AB. We see that AB is an element of R. So the next thing that we're going to check there, we're going to check if there's BA. You see right now? And if we check, is there BA? Yes, BA is there. BA is there. And then now we check AC. AC is there. Also CA is there. So I'm also going to mention that AC is an element of R, and also CA is an element of R. Right? Then lastly, we check BC. In other words, also CB should be there, which they're all there. So when we check BC is there, it's an element of R, and also CB is an element of R. So we see that when we take an element XY, YX is always there in that set, right? In other words, when I take AB, I must find BA, so I must apply commutativity, right? When I check AC, I must find CA in that set. When I check BC, I must find CB. We say, right? So it means that this set is symmetric. So this relation is symmetric. We can deduce that it is symmetric, but it is not reflexive, right? Then now let's check transitive. So let me erase this. We check for this to be transitive. Let's check for this to be transitive. What must occur? So according to the definition, for this to be transitive, right? For R to be transitive, we are saying that if we want R to be transitive, right? We should have, let's say we take XY. Let me say for XY, element of R, and also if we have a YZ element of R. You see right now, this should imply that XZ is an element of R. So that's the condition. In other words, if I have ABC and AB is an element of R and also BC is an element of R, by transitivity it means that AC should also be an element of R. We say, right? So in other words, we're going to come and check here now if we have those things. We first check AB. We do have AB. Say that B is an element of R. And now we check BC. BC is also an element of R. You see, since these two are related to B, it means that also A should be related to C. So we check if AC is there. AC is really there. We say, right? Then we see also that AC is an element of R. So in this case, since I'm proving, I don't have to write it then here. You can just come and say AC is an element of R. So we see that they are all there. Hence, R will be transitive. So I can write that therefore R is transitive. We say, right? So we know now that R is transitive and it's symmetric, but it is not reflexive, right? But if it was reflexive, symmetric, and transitive. Therefore, this will be an equivalence relation. Is that right? But since there is not, that we just see that. Then, now if you have any question, you can ask, right? But if not, we can proceed. So now we can go to B. We check B. So when we look at...
Sorry, can you please explain the reflexive part again?
Oh, okay, let me do this. Yeah, so for reflexive, right? So here's what I say. Say that here, for R, for the relation R to be reflexive, this says that if I take for each, or if I take for all X element of R, or not R, a set, our set is A, is not R, set A, it should occur that X should be related to itself, and that set should be an element of R. You see, right? That set should be an element of R. So, in other words, remember this simply means that X is related to X, is the same thing. So, when we come here now, we're going to check a reason. Remember here we have A, B, C, right? So we must check A, we check B, we check C. So when we check A, is there A in this set?
No, it's not there.
No, it's not there. But we have BB and CC, right? Which BB is this, CC is this. So we're going to come and say BB is an element of R, and also CC is an element of R. But AA is not. You say right, ne? That's why this thing cannot be reflexive. We say right, ne?
Yes, I understand.
Yeah, that's why this thing cannot be reflexive. So, means that now we can go to the other one. The other problem. So, when now we come to B, right? On problem B, here, we are given this. They say that we have R on Z, where X minus Y is equals to 4. We say, right, here they told us that X minus Y is equals to 4. And then they say the relation R defined on Z, where XY is an element of R, if and only if X minus Y is equals to 4. Then they say we should determine whether R is reflexive, symmetric, or transitive. So, for us to determine this, whether it is reflexive, symmetric, or transitive, first we'll check reflexive. And remember that for reflexive, we should take a definition. Remember, here the definition says where X, Y is an element of R. When we know that for this to be reflexive, we should say for all X element of R. You say right now. So we've proven from the previous one that X should be an element of R. If we take this, so in this case, in this type of proofs, we're just gonna take one element. We take X to be related to itself. You say right now. Or we say, let's say not even a pair. Let me just say X for all X element of Z. Let me start here. We can even start here. So the preferred one is where we start by picking an element from Z, and then we show what I have written there. We show that X is an element of R. So we can show this by saying, if I take X from Z, here, I'm going to say that this says where, according to the definition, it says that define R defined on Z, where, then I write the definition where Now this will be x, let me say this. So again, I'm trying to prove that x is related to x, right? So this, I see that this question, they've put it in this way so that people can start here. So what you're gonna do here, we're gonna say where we start here, want to check if x is related to itself. In other words, when I prove here, I should get that the left hand side is equal to the right hand side. We say right. So I'm gonna say x minus, I replace y by x. You see, this is equal to 4. But when we check here, is x minus x is gonna be 0, right? And this is equal to 4. Are these two sides equal?
No.
No. So it means that this simply implies that x cannot be an element of R, because it won't satisfy this one condition. You say right now. So it shows that this cannot satisfy the condition. So we said we picked x, we say where we apply the definition. So that's what we're going to be doing at all costs. So we must avoid starting here, right? First, you will pick an element from a set. Then you show by this definition to arrive here. You say right now. So if the definition is true, you can now deduce that this is correct. So the only one that can allow us to start here, it's symmetric and transitive, but the reflexive doesn't allow us to start here. I said right, you always start here. So let's do the one for symmetric and we see. Let me erase this and then we do the one for. So for, you see, so this thing is like this, right? I have reflexive. Here I always pick one element. Symmetric, I always pick 2 elements. Symmetric, usually always pick whatever that they gave you, right? And then transitive, I always pick 3 elements. So now I'm gonna pick 2 elements, which are an element of an integer. You see, right? For symmetric, now I'm doing symmetric. I say where. Now we see that x, y is an element of R. So this, the definition of symmetric, let me erase this thing and write symmetric since I'm proving symmetric. The definition of symmetric says, the definition of symmetric says that if this is true, then also this one should also be true. You say right there. So in other words, you must move from here to arrive here. So what the definition says here, what we're given from the definition, we're given that this is true if and only if x minus y is equal to 4. We say right now. So always for symmetric, we're going to apply commutativity. So I'm going to commute this 2, right, which this will be equal to 4. And this, I'm going to factor out negative. So remember, for us to show that y is related to x, this is the same thing as having to say, I decided, remember the original one was saying this. The original one was saying this. So if I write it like this, you can see where you're supposed to land, right? The original one was saying x minus y is equal to 4. So in other words, when I commuted, I replaced x by y, I replace y by x. So this should also give us 4. But if we solve here and find that it doesn't give us 4, therefore this thing cannot be symmetric. We say right now. So this is what we must show here. So let's just show here and then we'll check that. This is equal to 4. And when we divide both sides by negative, we're going to get x minus your y minus x, which is this side, right, which we wanted. It's this side. Then we want to check if the other side, when we divide by negative, we get minus 4. You see that this side is not the same as this one, right? So we were supposed to get that y minus x is equal to 4. But since this is not true, this is not satisfying the original definition, then we must come and say, therefore, y x is not an element of R. You see, right? In other words, R is not symmetric. We say right now. So R is not symmetric. So that's the case. Did you understand this one? So
Yeah. Something like that.
All right. So I think you'll see when we do the other ones.
Okay, so
yeah.
okay, I wanted to ask me the reason why it's not symmetric. It's because of it's not y minus x equals to 4. Instead, it's y minus x equals to minus 4.
Yeah. That's the reason.
Okay.
Yeah.
Okay.
So now we can check transitivity. So for transitive, we're gonna take three elements. We always check 3 elements. We take x, y, z, which is an element of an integer. And then here we're going to say where, remember, x should be related to y and y should be related to z. That's the definition of transitivity. Alright, so first we're gonna check that. We take that xy element of R. Alright. And so this will be if and only if x minus y is equal to 4. Then we say and. Now we take y related to z, which this means that y minus z should be equal to 4. Now here we're going to say then, now want to prove is x also related to z, because they're both related to y, you say, right? So it means that they should be related. So want to prove that. But for us to prove that, it's either we add these two. You see, I get you said this one has a negative here, right? So it's either we add them or we subtract them. So if, let's check which one would be correct. I think if we add them, right? So if I add these two, I take x minus y plus y minus z will be equals to, then 4 plus 4 will be 8. We agree, right? And then this will be x minus z. This doesn't give us 4. You see, right, ne? It doesn't give us 4, it gives us 8. Hence, it means that x cannot be related to z. You see, right? X is not related to z. Other words, z is not an element of R. So this, we realized something. This is not reflexive, it's not symmetric, and it's also not transitive. We say, right? So that's what we get from this question. So did you also understand this one? Let me change this because it's transitive, right?
Yes, I did understand.
All right. So it means that now we can go to the other one. Let me erase. It means that we can go to the other one. Now, when you come to this one, they say a relation R defined on N, where Mn is an element of R if and only if M divides N. Then they say we must check if R is reflexive, symmetric, and transitive. Right? Now, when you come here, we say that first, a relation R defined on N, right, where this, so must check reflexive. So we're gonna check the same way. And first we must understand what does it mean. What does it mean M divides N? Do you know what does it mean M divides N?
No, I don't.
So it's either this or this. Which one do you think is correct? The M divides N.
The first one.
M divides N. The first one.
Yeah. Yeah.
Oh, why do you think that one is the correct one?
Because the statement says if and only if M divides N. Because, okay, let's say for instance, M is 0, ne? 0 divided by anything, it's 0. So, and then if n was, okay, it's 0. And then there in the second one, m is 0. So we know that anything divided by 0 is undefined. That's what I think. Maybe that's why it's correct.
M divides n. So then what is m divide n? You know that these are different, right?
I didn't know.
This one, m divides, it means that m is the one that is dividing n.
Oh.
You say right. So it means that the second one is the correct one. You say right. So m divides n, yeah. Or we can also write it like this. When what we mean by m divides n in mathematical format, in this case, it means that they should exist, right? There should exist some integer k. This should be an element of an integer. So this will be such that we're going to have n is equal to mk. You say right now. So this is what we're going to have.
Please repeat what you said.
They exist an integer k such that n is equal to mk.
Oh, okay.
And this is the same thing as saying that, let's say maybe we say that m is a factor of n. You say right now. And also it's the same thing as saying that let's say we say that n is a multiple of m. So they can bring it in these two ways. You say right now. So in this way, we are going to say, now for us to show a reflexive, so for us to show that this thing is a reflexive, we are going to come here and say, here we're given, they say this should be defined on n. All right. So I'm just going to take an element. So when I take an element, this element will be, let me say, here we're given m and n. So I'm just going to take one element there. So I can say, let me say, for all a, m, which is an element of a natural number. You say right now. So when I take these unnatural numbers, so here I'm going to say that using the definition says that m should divide n, right? So in other words, I must have that m should be equal to mk. We agree here right now. M should be equal to mk. So when it's in this case, we are going to say this means that if I divide both sides by m, I'm going to get 1, which is equal to k. Is 1 an element of an integer?
Yes.
Yes. So it means that this is correct. We say right now, because this, when we say m is equal to, remember from mathematical induction, when you are assuming pk to be true, you're saying that this is true for some k. In other words, even if it's one element, it will be correct. You say right now. So now,
Yes.
we're saying therefore mn is an element of R. Hence, and we say hence R is reflexive. We say right now.
Yeah, I understand.
Then when we come to symmetric, for symmetric, so for symmetric, we're just going to take two elements as we're given. They were given m and n. This is an element of a natural number. Then the formula says this. The formula said that m is equals to, not m, n is equals to mk. You see right now, which is what we had there, that m divides n, which is in this case. You see right? Or in other ways, I would write it like this, but at the end it will become this when I multiply both sides by m. So
Yeah.
when I have this, now I should commute. You see right now, I should apply commutativity for me to get to the solution. So let me erase this. So I should apply commutativity for me to get to the solution. So here, the aim here is to arrive on this. Remember, if this is the case, it means that for reflexivity, I must arrive where, for symmetric, I must arrive where m is an element of R, meaning the opposite of this. You see right? And that will happen if and only if n now should divide m. You see right now? So this should be the case where I should arrive. So for us to arrive there, obviously we're going to say this is equals to k. This will be the easiest way to commute. When I commute this, I'm going to have m over n, because this is where I must arrive. You see right? Where n should divide n. M, yeah. And then this will be equals to 1 over k. So if we check this, is 1 over k an integer? Let's say I agree we took k as an element of an integer, so 1 over k will become an integer. Will it be an integer? No, right?
No.
Because we don't have fractions and integers, right?
Yes.
And we know that this is not an element of an integer. Hence, m cannot be an element of R. Hence, R is not symmetric. We say right now. So,
Yes.
now we can check transitivity. So now when we check a transitivity, instead of picking 2 elements, we're going to pick 3 elements. So we're going to pick mn, p, which is an element of natural number. So we take m is equals to we take n is equals to m. It means that we're going this side, right? Then we take p and p is equals to nk. No, let me say nk. Let me say np, because I can't choose the same integers. For some p element of an integer. So in other words, I took that m divides n, and also took that this one n divides p. So if this is the case, therefore we should prove that p should divide m. You see right now. So if m divides, not p, man. If this one, let me write like this so that it can be visible. We have mn, which we take mn, then we take np, then we take mp. Yeah, so this way we must arrive. First we took that m divides n, then we take that n divides p, then m should divide p. You see right? If that's the case. And then now we have this. I already have p here. Another thing which I can say, I can't choose p since I've already chosen p. Let me choose another. I can choose what? R, right? Because we don't have r. I can't choose this as an element and also as an integer. Yeah. So now we have this. We have chosen that m divides n, and also n divides p. So in other words, we are saying that if n over m is equal to that, and also p over n is equal to that, it means that this can give us what? P over m according to calculations. You say right now. So now we must arrive here, which is this. M divides P. You say right. So that's where we must arrive. So this one, remember this one of divides, it's either, remember I said that it's what? It's divide, multiple, or a factor. So it means that instead of adding, remember with the previous one, for us to find transitivity, we had to add, right? Then now instead of adding these two, we're just going to divide them or multiply. So the easiest way to get there is if, in this case, we see that we have, if I come and say this implies, let me say this, n times p will be equals to m k times nr. You see right, so I'm just gonna multiply these two because they say this they divide. You see right now, so we're just gonna multiply them. Then you can do n. If you want to also change them first, you can change this to n over m to be like this so that you multiply. At the end of the day, you must arrive here. Remember this says what? Says that m divides p. So it's gonna be like this. So you must check, how am I gonna arrive here? Should I multiply or divide? So you check which one is best. So I realized that for me to arrive there, it's if I multiply. So with this case, this will mean that when I divide both sides by n, I'll get that p is equal to mkr. And this is it right now. So this will be p is equal to mkr. And kr are integers. So when we multiply two integers, are we going to get an integer if we multiply two integers?
Yes.
Yes, so it means that this should be an element of an integer. Hence, this means that m divides p, because I can divide both sides by m and then it will still be correct. You say right? And then this should be an element of r. Hence, r is transitive. We say right? So one of these, you're going to be writing a quiz about them when we open. You're going to be writing a quiz. I just took this from your tutorials. You're going to be writing a quiz about all this. How many tests have you written? You have written 3 tests so far, ne? Is it 3?
Yes.
Yeah, you guys are left. I think you're left with 2 tests. Unless if they decide to give you a test for a makeup test at the end. So I think people think they still have time, and if you try to check, if you qualify with nothing, if you qualify with less than 60, you might be in trouble. So they're not seeing that at the time being. So when it comes to relation R defined on real numbers, where x is related to y, if and only if x is less than y. So we're gonna end with this one, right? Then you're going to try this last one. So now when I come to this one, so let me yeah, that's fine. Let me erase this. When you come to this one, they say if we have r on real numbers where x is less than y, we must determine whether r is reflexive, symmetric, or transitive. So for us to determine this, right, for reflexive, as to determine reflexive, we must do this. We must say for all x element of a real number. So I'm taking x from real numbers, and I said that we must start here, right? We must start by showing this. This will occur if x is less than x. Is x less than x?
No.
No. We say right now. So we say that this is not true, right? X cannot be less than x. So this is not reflexive. So we say that which is not true. Hence, let me not say hence, let me say therefore, x, since here we're using xry, right? X cannot be related to y. You say, right? Hence, R is not reflexive. So R cannot be reflexive here. Now we can check a symmetric for this. So now if we are supposed to be checking a symmetric for this, we're gonna be saying this, we're gonna say for symmetric. Now let me erase this. We use symmetric and see what you're going to get. So for symmetric, we're gonna take two elements. Remember I said that for symmetric, we always take elements that we're given. We're given x and y. So I'm gonna take xy, which is an element of R. Now this happens where x is related to y. If and only if x is less than y. So the aim now is to commute. Remember I said that for symmetric you always commute after writing this definition. It's like you take the original definition, right? Then you start commuting to see if now when I commute I must get that x, your y is less than x for this to be y related to x. So I must arrive there. Now let's see, when we commute, take y to the other side, x to the other side. And then when we divide both sides by negative, we get that y is greater than x. You see, we didn't arrive where y is less than x. So it means that this is not symmetric. We agree, right now?
Yes.
Yeah, so we didn't get where we wanted to get. So it means that hence R is not symmetric. So now we come to transitive. We can come to transitive. For transitive, remember we're going to take three elements. Right, for transitive we're going to take three elements, and we take this first element and also another element. So we're taking x, y, z, which is an element of R. So we took the first element where x is related to y. Then we must take where y is related to z, if and only if y is less than z. So this says that for this to be true, x must be less than z. I mean, otherwise x must be related to z. And then remember, for us to get that, it's either we add or we subtract or we multiply or divide. But the best way to get there here is if we can add these two, right? We can say x plus y is less than z plus y. And if I take y to the other side, this will be what? X is less than z. And this is true. We agree, right now? So wanted to arrive where x is less than z. So we say hence this means that x, let me write like this, x is related to z, hence R is transitive. Yeah, so I'm gonna leave the last one as an exercise, and then I see what you guys are going to get from there. So yeah, so I think that's it. Let me just stop the recording.